Good morning, class. We are looking at quadratic algebra practice test number 2, module 2, covering chapters 3 and 4. Here's chapter 3, functions, the second part. Extrema. It's the plural of extrema. Maximum or minimum points on a curve. Local, also known as relative extreme values. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of A to B in the domain if f of c is less than or equal to f of x for all x values in the open interval. A local maximum is the maximum value within some open interval. Local maximum occurs at a point C in an open interval of A to B in the domain if f of c is larger than or equal to f of x for all x values in the open interval. So let's take a look at this. This is the local max, this is the local mean. Again, local mean, local max, very straightforward. Peaks are considered to be max, valleys, or minimum. Now, absolute, also known as global extreme values, or extrema, are either maximum or minimum points on a curve. Absolute minimum occurs at a point C if f of c is less than or equal to f of x for all x. This is in some open interval. This is for all x values in the domain. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. So as we look at this, in fact, let's look at them together. Local mean, local max, local mean. This one is also absolute mean. Why is that? No other point has a smaller y coordinate. Local max, local mean, local max. This local max is also an absolute max because no other point has a y coordinate larger than that. So it's important to understand the concept. Now, use a graph to estimate the intervals where the function is increasing or decreasing. If function f is increasing on an open interval, I, if for any choice of x of 1 and x of 2 in I, with x of 1 less than x of 2, we have f of x of 1 less than f of x of 2. A function is decreasing on an open interval I if for any choice of x of 1 and x of 2 in I, with x of 1 less than x of 2, we have f of x of 1 larger than f of x of 2. A function f is constant on an interval I if for all choices of x in interval I, the values of f of x are equal. In short, for the increasing part, or for the decreasing part, as we go from left to right, x gets larger. But what about the y? If the y value gets larger, we say it's increasing. If it gets smaller, we say decreasing. So if you look at the portion that looks almost like a line with a positive slope is increasing, same thing here. This is the portion which is decreasing. So the function is decreasing here. Increasing here. So increasing, this stops here. So seems to have the x coordinate of -8 all the way to this point. If you look at it, it's -3, and then starts from here, which is +3, stops here at about number 7. And in between, from -3 to +3 is decreasing. I'm going to erase this so it becomes easier to see. So this portion is increasing. The x-coordinate starts from 8, and the x-coordinate for this one is 3. And -3, this is +3, and this is +7. So from -8 to -3, union 3 to 7. And you always use parentheses, not brackets, always. And decreasing is here, or you can say x between -3 and 3. Any local max or mean. Peaks and valleys within the domain of the function are considered local. They may be absolute also, but what's important, the end points can never ever be local. So this is a local max, this is a local mean. So local max is equal to the y-coordinate 50 and seems to be taking place at what point? -3. Therefore, we write local max is 50 at x equals -3. Sometimes they want you to write the pair. Sometimes they want this one. Sometimes this one or all of them. What about local mean? It's here, this point, and this point has a y-coordinate of -3, -50 with the x-coordinate of +3. So local minimum equals -50 at x equals 3, and you can write it as a pair, 3 comma -50. Determine any absolute max or minimum value. The function has no other place having larger y-coordinate than this point. This is the absolute max. No other point goes down more than this one. So absolute max, absolute mean. Absolute max equals what? 150 at x equals 7. Absolute max is 150 at x equals 7, or you can write 7 comma 150. Again, you want to pay attention how they want you to answer it. Here's the location of an absolute minimum, and it seems to have y-coordinate of almost -225 and the x-coordinate of -8. So absolute minimum is -225 at x equals -8, or you can write it as -8 comma -225. Okay, so I hope it's clear to everybody. For the following function, f of x equals 2x minus 7, find f inverse of x. Let's go through the process. Number one, we are going to call this y in order to make it easy to work with that. Number two, interchange x and y. Right here, we have the inverse. However, as you know, we always solve for y, which means we're moving -7 to the other side. So add 7 and then divide by 2. And y becomes x plus 7 over 2. We call it f inverse of x. Now we know that f inverse of x equals f inverse O f of x equals x. So we want to prove we haven't made a mistake. It's always a must. So we are going to look at one of them. I highly recommend you look at the second one. So let's look at f inverse of x, which means replace the x with f inverse, which is x plus 7 over 2. These two cancel each other. X plus 7 minus 7. These two cancel each other, equals x. And that's a proof. We are going to do exactly the same thing for the function f of x equals x over x plus 2. And we are going to start interchanging x and y. So to do that, first we gotta call f of x y. Then we change the y to x, x to y. We interchange the two. So right here we have the inverse. But to solve for y, we are going to do the cross product and solve for y. So this gives us x times y plus 2, which is xy plus 2x, and this gives us y. Since we want to solve for y, we move this one this way, becomes negative. It's better to actually move this one this way. This way we have the least number of negatives. So let's move the xy and make it negative on the right side. It makes it negative xy. On the right side, we can factor the y out. And all we have to do is to divide both sides by 1 minus x. And we get the inverse function. We call it the name f inverse of x. What I like to add here is the following. Depending upon how we move this, remember, even right here, you could move the y to the left and 2x to the right, you end up with this format. And please understand, these two are the same. So depending on how you moved it. Why are they the same? So if you multiply this, the top and the bottom by negative, this becomes minus 2x, this becomes minus 1 plus. So that's either way. Now, their composite function must be x, and we can look at that to show that we haven't made a mistake, everybody. Which means for this function, we're going to replace the x with either this one or that. Let's do it with the green. F of inverse of x. Replace the x with 2x over 1 minus x at the top. at the bottom. And this is a complex fraction we are going to simplify. How do we simplify? We multiply the top and the bottom by LCD, which is 1 minus x. What happens is this. If you multiply these two, they cancel each other. The product of these two is just the numerator. So the product of these two is just the numerator 2x. The product of these two, the same thing. It's just the numerator 2x plus 2 times 1 minus x. Plus 2 times 1 minus x. And we are going to simplify it. Everything remains the same. This one we distribute, we get 2 minus 2x. These two cancel each other. We get 2x over 2, which is equal to x. And that's the final answer, everybody. Use function composition to verify that f of x and g of x are inverse functions, where f of x is the cube root of x minus 1, g of x is x cubed plus 1. And as you know, two functions are inverse functions if their composite function is x. As long as you show either f of g or g of f is x, that proves that because this composite function can be done in any order, f of f inverse or f inverse of f. So let's look at f of g of x, which means replace the x in the f function with the g. So cube root of square root of x is replaced by x cubed plus 1. And this is the negative 1. These two cancel each other. Cube root of x cubed is x, and we are done. Let's quickly show the GOF of x equals x as well, which means for this function, replace the x with the f. Replace the x with cube root of x minus cube root and the power of 3 cancel each other. This comes out as x minus 1. These two cancel each other, and we get x. Sketch the inverse of the function whose graph is given. Draw the line y equals x and reflect the graph on the line. So this is y equals x. How do you do that? Well, the best course of action is to pick some easy points from one function and get the pairs for the other one. For example, if AB, remember, A comma B is an element of f of x, that means B comma A is an element of its inverse. Therefore, let's pick up a few easy pairs. So as we look at this point, it's easy to read -2 comma -4, and it's on the graph of the red line, red function, okay, or f of x. In short, and that means an element of this is red and element of, that's how you read that. In short, the -4, -2 is for the inverse. That's all. Now, the way you could write it is f of -2 is -4. That's the meaning of it. So f inverse of -4 is -2. Or simply put, -4 comma -2 belongs to f inverse. So locate -4 -2. So you got 1 point. We continue with more points. For example, 0, 4 is an easy point. It's the y-intercept for f of x. And clearly 4, 0 must belong to the other one. But let's write the meaning of this f of 0 is 4. That means f inverse of 4 must be 0. And as I mentioned right here, 4, 0 must belong to the inverse function. So we locate that. Or 0. Let's look at another easy point. Clearly, this point is on the function f of x located at -1, +3, which means 3, -1 belongs to its inverse. So again, to elaborate on that, we write f of -1 is 3, which means f inverse of 3 must be -1, which means, as I said in the beginning, 3 comma -1 belongs to the inverse. And so you locate 3 comma -1. This is 3 and coming down by 1 unit is that. And if it's not enough, you can always look for more points. Okay. One easy point that is important to understand is that if the function ever crosses the line y equals x, the other function must also cross there, because X and Y interchange, and any point on the line Y equals X, they have equal X and Y coordinates. So this point, and I made it huge, it's always the case. So if any one of those graph crosses a point on that line Y equals X, the other one must also cross. So you can see it goes like that, looking like that. We're going to move on. So a quick recap. You are given a graph, draw the line Y equals X, pick a few points on the graph of the function that is given, and just change X and Y, make it a point for the inverse. If over here we have 1, 2, 3, and the one in common, or if that's not enough, pick 2 more points, 3 more points. You can easily see the graph. Okay. But it's important to pick up easy points so you can easily read it from the graph. Okay. Sketch the graph of the function f of x, evaluate a few points, and determine the domain and range. First, I want to show you how you pick a few points, and if you just plot those points, really does the job. Then I want to show you the way I approach this that makes life easier. Number one, some points. Okay. -1, 0, 1, 2, 3. You can pick, again, we are going with easy points. You can pick -2, -3, +4, +5, a few more points if you, but anyways, just a few points to see how they are calculated. So to understand this, this is a piecewise defined function that has 1, 2, 3 pieces. In essence, the top piece is the line y equals -x plus 1. The second piece is just a pair, okay, with x coordinate being 1. So right here, x coordinate being 1, the y is 2. So this is given. This is the pair 1, 2. Again, let me just first show you the meaning of this. Class means the pair 1, 2. So you already have this one as true, 1, just to give you an idea. Now, what about the rest of it? It says this is good as long as x is between -1 and 1. Is it equal to -1? Yes. So if I put -1 here, I get minus -1, which is 2 and 1, minus -1, which is 1 and 1, 2. What about 0? 0 also belongs here. 0 also belongs here. 0. So if I plug in 0 here, I get 1. What about 2? X larger than 1. So you put it here, 2 squared, 4. What about 3? Again, the same thing because larger than 1. 3 squared is 9. So the pairs are -1, 2, and the rest of it. So those are the pairs. And you can plot those pairs and they will help you with the graph. No questions asked. However, the way I approach it is that I do all 3 parts. And first, I don't pay attention to the restriction. Of course, this is just one pair, 1 point. So let's graph this one. which is a line y equals negative x plus 1. And we have the pairs. The line, the top one, everybody. This means this line, y equals negative x plus 1. Obviously, if x is 0, we get 1. If y is 0, we get 1, 0. And what I'm going to do, I'm going to graph the line, and I'm not going to even look at this for now. So 0, 1, 1, 0, and that's the graph. 0, 1, 1, 0, that's the graph. Then we have the point 1, 2. Then we have the parabola f of x equals x squared. I'm going to call it y equals x squared. And as you know, a parabola looks like that, right? So you graph it. Again, we are not paying any attention to that restriction. This is not the answer to the question. So how do we make it an answer to the question? We pay attention to the restrictions now. So one piece is the top piece. The second piece is one pair. The third piece is a parabola. How do we do the restriction? We start with the line. It says it's good from -1 to 1. So from -1, and you know at -1, we get 2. So from here it's good. All the way to 1 here, but it's not equal to 1. So we get a solid point here and a hole here. So this portion of a line, that means this blue line, all of it is gone. This is gone. This is gone. The only portion is this part. This is a solid point, and this is a hole. Okay, everybody? What about the green parabola, y equals x squared? Let's work on that. It says it's good when x is larger than 1. So first of all, if you plug in 1, you get 1. So right here, everybody, there is a hole because you don't have the equality, because at 1 it's 2. So you put a hole at, so again, you plug in the hole at 1, 1, and the rest of it is fine. There is a hole at 1, 1, plug in 1, you get 1, 1. And this portion is good. The rest of it, it's not. In other words, let me this portion, none of it is good. So what is the graph when put them all together? Looks like this. So this portion of a line, solid point, hole, this portion of a parabola, hole goes up, and this point is this one, and you're done. Now, what about the domain and range? Domain starts from, if you remember, drop it along the x-axis. This covers -1, and this point covers this point. So from -1 to infinity. So break it along the x-axis. You get this one. And the range, break it along the y-axis, starts from here, goes up. But here, I don't see anything covering it because there's a hole here. So although it goes from 0 to infinity, 0 is not covered. So we get a parenthesis for 0. Bracket for -1, parenthesis for 0. If you can follow it, it's as difficult as it gets, and you'll be fine with this concept, okay? Find the average rate of change of f of x equals x squared minus 3x. F of x equals x squared minus 3x from x equals 2 to x equals 4. And remember, it's basically rise over run, f of b minus f of a over b minus a, or f of 4 minus f of 2 over 4 minus 2. That's the meaning of it, everybody. Average rate of change means you have 2 points, the difference in their y coordinates over the difference in their x coordinates. In other words, connect the 2 points, calculate their slope. That's the meaning of average rate of change. So basically plug in 4, you get 4 squared minus 3 times 4, minus plug in 2, you get 2 squared minus 3 times 2. The denominator is just 4 minus 2 or 2. So let's evaluate this. This is 16. This is minus 12 is 4. This is 4 minus 6 equals negative 2. With this one, we get positive 2, and we get 6 in the numerator. 6 halves or 3. Find the average rate of change of f of x from x equals 4 to x equals 4 plus h. It means f of 4 plus h minus f of 4 over 4 plus h minus h. In essence, we are using this, everybody. So the denominator, this is minus 4. The denominator is simply h. Let's look at the numerator, which means we are going to plug 4 plus h into this function. We get 4 plus h squared minus 3 times 4 plus h. And then we plug in 4. If you want, you can even use f over 4 here, which we had come up with 4. Either way is fine, or just write 4 squared minus 3 times 4. Either way is fine. So this is a plus b squared, which is a squared plus 2ab. Let me just remind you. A plus b squared, which is a squared plus 2ab plus b squared. So 4 squared is 16 plus 2 times 4 times it. H is 8h plus h squared minus 12 minus 3h. And as I said, just minus 4. Or you can say this is 16, this is 12. Normally, we want to do them in the brackets, but this is 16. So minus 16, this is 12 plus 12. And the reason I actually want to look at it this way, because this number, this number, this number, and this number, take a look. 16 cancels out minus 16, 12, and negative 12. So what we are left with in the numerator is h squared eight h minus 3h, also giving us 5h. So the numerator, we can factor the h out. We can cross the h, and we end up with h plus 5. Now, this is extremely important for you to know and be able to handle, because later on in calculus, you take the limit as h goes to 0, you set this equal to 0, and this becomes 5. So it's important to be able to handle simplification of a difference quotient, everybody.